have functional groups, and how do you interconvert them to different functional groups. Okay. So, here's a molecule right here, you have an alkene, okay? But I want an alkyne. Prof Yusuf's question on the midterm says, I want an alkyne, and you start with an alkene. So what kind of chemistry do you know? So you start out with an alkene, over here, you're adding this bromium to it. We know what happens, you add bromine Br2, you form the 3-member ring, right? You form the 3-member ring, bromine plus, then the Br minus comes underneath and hits it, and you get a trans Br2. Okay, so that's what you have here. So you add a bromine, you get this reagent. You're like, what the hell's happening here? He's going from a double bond to a single bond. Okay, but he's asking to get up to an alkyne, which is going up the chain. So the double bond, we add the bromine, we get this situation over here. Then we add a very strong base, potassium hydroxide, OH minus. What is the OH minus going to do? It's going to rip off this proton, it's going to go here and knock out this bromine. So you get a double bond again. Then it takes this proton, rips it off, brings it down, takes off that bromine, then you get the alkyne. Okay? Everybody all right with that? Let's see some furrowed eyebrows. OH minus. Bada bing, bada bang. There it is. Right? Just attacks that proton, rips it off, goes in there, and then the bromine leaves. Okay, they have to be trans to each other, but it's the H and the Br. You can just kick it out. Is that okay? That's the first reaction, right? The OH minus comes, rips off one H. Those electrons go into, make a double bond, and the other bromine comes out. You get HBr down.
If you put one KOH, could it stop at the alkene?
Yeah, it'll stop right there.
It's not there.
That's why they said 2 equivalents. So he made an important distinction. It says 2 moles of potassium hydroxide. He's ahead of the game. If I said 1 mole of potassium hydroxide, that OH minus is only 1 mole, 1 equivalent. So it only can do it 1 time, then it's done. There's no more OH minuses around. It just says it 1 time. Okay. This one here says 2 moles of potassium hydroxide. So the hydroxide can do the first one. There's still an equivalent of OH minus around that can do the second one. Then you have the second OH minus. That's going to attack this. Bang, bang, bang. And then you get the alkyne. Okay. So if I say make an alkyne, you're like, I really don't know that much about alkynes, but I know that if you have these 2 halide groups across a single bond, I can add 2 equivalents of a base and it'll just knock both of them out and make an alkyne. Okay. Started off with a double bond, we went down to a single bond, then 2 equivalents because we can, down to the bromines, and we get our alkyne here. Okay, you have to know this reaction. It's pretty straightforward. What's another reagent that you can use? Now we're starting with a double bond that has a halide right across it. You could add this sodium halide, called sodamide. It's a very strong base. This NH2 minus is a very strong base. Now everyone knows when I say base, that means it's going to rip off a proton. When I say nucleophile, it's going to become part of the molecule. It attacks the molecule and becomes part of the molecule. A base rips off a proton. Bronsted-Lowry definition of a base. Rips off a proton. Okay. So sodium halide is a very strong base. It's looking, it's a minus, it's going to look for a proton. There's a proton, it's going to come in here and kick out the chlorine, just like the second step over here. Okay, so you can go directly to the alkyne. Okay. Now there's a distinction over here. Look at this molecule here. I have an OH over here, a hydroxy group. Well, I have a sodium. Why didn't it rip off this proton? Which one is more acidic, this OH or this H? right? That's what it's telling you. This sodium amide sees this molecule. So the amide is floating around the room. It's an NH2 minus. It's like, I really am looking for a proton. I'm looking for the biggest delta plus proton around so I can rip it off. Okay? It encounters this molecule over here that's floating in the room. This is floating around. When the amide approaches it, what does it see? It doesn't see chloride, hydrogen, double bond. It doesn't see any. It just sees electron density. It just sees delta pluses and delta minuses. And it's going to go right for the biggest delta plus. And that's the hydrogen off of the alkene. Because it's pulling electron density towards it. You're going to see that in a slide or two. Okay, that's why that's the most acidic proton. This one versus this one. Because when the proton comes off, you look at this is O minus, and this is the minus here. This minus is actually more stable than this O minus here. That's why it rips off this one, and it comes in and kicks out the bond. Okay. As I mentioned before, you see a molecule, you look at the molecule, you go through your little list of stability of that molecule, everything you know about that molecule. One of the things you think about is that molecule an acid or a base? If it has protons, it's an acid. Some of those protons are ridiculous. They're never going to fall off, but like really weak acid. But you look at all the protons and say, oh, I think that is the one that is probably going to be the most acidic. Okay, so when you do these nucleophile-based type of reactions, you're like, not a problem. I know that's the one. Okay, so I'm guesswork. Review. You have this molecule here. Are all the protons equivalent? Not really. This is a primary carbon, so 3 hydrogens here. This is a secondary 2 hydrogen. This is a secondary 2 hydrogen. This is a carbon primary. It's 3 hydrogens. Are all these hydrogens equivalent? When I look at this molecule, do I see any resonance structures? Remember I told you? As soon as you look at all of those things. Is there any resonance here? Sure. There's double bonds right here, so you just break them up. So you need a minus and a plus, minus and a plus. That's extreme, right? You're just looking at the molecule. Oh, there's plus charges over there. They want electron density. That's why these 2 protons right here are way more acidic than these protons here. Does everybody agree with me? Those protons are much easier to pull off because when you get a minus charge here, they delocalize into 2 different carbonyl groups, right? They can move back and forth between them. That's why those 2 protons are very acidic, considered. So if you add a very strong base, it's going to pick up those protons. Okay, this is a review. But remember, when you see a molecule, you got to go through the whole list. Is it an acid? Is it a base? Are there any acidic protons? Is there delocalization? Is there resonance? Stereochemistry? Dipole, right? You go through your little list of the molecule and you see everything. Okay. No problem there. Here's a reaction of alkynes. What do we got here? So here's a terminal alkyne. We add HX across it. It's an acid. HCl, HBr. What's going to happen? This is a nucleophile. It's going to attack the electrophile, the proton, right? It's going to attack. You're going to get what? It's going to attack. You're going to get a carbocation on the secondary one, which is a vinylic carbon. You can get a plus charge there. That's why the X comes in. You can do the reaction again, HX. This will go and pick up a proton. You're going to get the carbocation again over here. And then the second X is going to come in. And you form this geminal dihalide. Geminal means on the same carbon. Geminal. Twin. Geminal. Okay? On the same carbon. So if you have this molecule right here, this geminal dihalide, you know that, oh, maybe it came from an alkyne. So we just added 2 equivalents of HX. Okay. Everyone understand this one here? Plus charge here. Everyone understand this is the first intermediate? Yes? so it is an X, the X then minus right comes in. And you get this molecule right here. Everyone understand the next one? This will attack at H plus